We have seen that at a given temperature, the equilibrium constant is always constant. So for example, in this reaction, when hydrogen and iodine combine to give two molecules of hydrogen iodide, the equilibrium constant is equal to 50. Okay, and in this case, because it's larger than 1, you can assume that it's a more product-bound reaction, etc. Because the equilibrium constant is constant, that does not mean that the concentrations in equilibrium are always the same. In other words, depending on your starting point, the concentrations of equilibrium will be different because there are different numbers that when combined can give you 50. Let me give you an example. In this case, if we start with 0.50 molar of only reactants and no products, and we allow the reaction to evolve towards equilibrium, you will end up seeing this distribution of concentrations, and as we said, you'll have more products than reactants. However, if you start with 0.50 molar of only products, notice that the concentrations in equilibrium are different. And this means that the concentrations in equilibrium are not necessarily constant. What's constant is only the equilibrium constant. And likewise, if you start with reactants and products all in the same concentration, you will still have an evolution towards equilibrium, and you'll still always have more than reactants and products, but again, the concentrations in equilibrium are different. Okay, so how can we find concentrations in equilibrium, or what is the general strategy to calculate the concentrations in equilibrium, or to calculate the equilibrium constant given some concentrations in equilibrium? To do that, we need to build the so-called ICE table. So, and we will show you an example to exemplify this this ICE table strategy. In this case, it tells you that we have a flask of 2 liters. Notice that all of them are gases, so they will all be homogeneously mixed. And you start with 0.2 moles, so that means that the concentration of HI initially is 0.2 moles over 2 liters. In other words, it's going to be 1 molar. Okay, and this is allowed to evolve towards equilibrium, and it's asking us what is the equilibrium constant value given that at the end you have this much left of hydrogen iodide of the reactant. So let's build the so-called ICE table. Here you have a balanced reaction. It's important to understand also that the equilibrium constant, because all of them are gases, so you will have products, concentration of products over concentration of reactants, and let's never forget the square because we have a 2 in here. So how do we build the ICE table? Initially, what do we have? Initially, we have 0.1 molar of reactants, and doesn't say anything about putting in the flask any products. Now, once it reaches equilibrium, what will be the extent, and of course you may have seen that this is going to be evolving towards the right. There's no way it can evolve towards the left because we don't have any products. So what will be the extent to which these reactants will evolve towards products? I do not know, so I will have to, whatever that, if I call this X, X will be the amount of products being created to reach equilibrium. How much will have been disappeared? It will have been disappeared. So notice that the ratio is 1 to 2, so there will be negative 2x. Okay, so if it's 50% created here, there will be 2 times 50% in here. Okay, so in equilibrium, this means that whatever that is, whatever the value of x is, this will be my concentration in equilibrium. I had initially this much changes, what is left is initial minus what it has changed. And because I had 0 initially, what I have in equilibrium, 0 plus x is x, 0 plus x is x. Okay, so notice that the equilibrium constant would be x times x, right? Concentration of hydrogen times concentration of iodine divided by concentration of hydrogen iodide square. Now, what it's giving us here is that in equilibrium I have this much concentration left. So this means that 0.1 negative 2x is 0.078. That is my concentration in equilibrium. This means that 0.1 minus 0.078 divided by 2 is equal to x. And I don't know if I need a calculator here. This will be 0.022 divided by 2 is 0.11 molar. Okay, that's my value of x. So this means that what I have here is 0.011 times 0.011 is 0.011 square, and this will be 0.078. That is the concentration of iodide square. There you go. We found the concentration in equilibrium. We have found the value of equilibrium constant. Okay, we will solve more problems than that, so stay tuned and you'll see how many applications the building of the ice table has.